Okay, we are good to go. Fine. So, hello, welcome you all to the seventh week's discussion for this NPTEL course titled Multirate-DSP. Myself, Saurashis Chatterjee, a PhD scholar from IIT Kanpur, and today we are going to solve a few problems based on the content of the lectures on week 7. As we have seen in lecture from week 7 consists of roughly delves on following topics. First of all, of course, all-pass filter and its properties. Today also we are going to solve at least 3, 4 or more than that number of problems. We are basically hovering around the properties and design of all-pass filter and see exactly what is happening in all-pass filter based on different situation. Second is we have saw few different kind of transformations, namely lossless, sorry, not transformation, transfer function, we have seen lossless transfer function among many others. Third topic we dealt with perfect reconstruction, and fourth is brief introduction to capacity of AWGN wireless channel. Okay, one of the transfer function is bounded real transfer function. The problems we are going to solve today are mostly around all-pass filters and its different properties, which and there is some question based on the capacity of AWGN wireless channel also. We have also seen decomposition of a transfer function into a simpler module and analyze them. There is one or two questions based on that concept also. So let us start. Okay, the first question, you have a transfer function hz, which is represented as like this, and the question asks that which of the following is accurate conjugate of hz. So if there is a transfer function of this form, hz is equal to A1 plus B1 Z inverse conjugate of AZ, which let me denote as H1 of Z, is nothing but you take the complex conjugate of each of the complex quantities in the expression of AZ basically. So A1 and B1 can very well be complex coefficients. They are generally. Therefore, if the complex conjugate of A1 denoted as A1 star, H1Z is going to be A1 star, B1's conjugate counterpart B1 star, and also Z's conjugate version Z star minus 1. So the problem expression, we have H Z to be 1 minus 6 J plus 7 plus 6 J times Z inverse. So conjugate of that, we denote it as H1Z. It is nothing but AZ conjugate I just simply take conjugate of all the complex element present in the expression. That's it, nothing more. So 1 plus 6j's complex conjugate is 1 minus 6j. The real part remains same, of course. You just change the sign of the imaginary part. That's what complex conjugate is. So check which of the expression goes with the following. Now in the question it is 1 minus 6j. Let me correct myself. Therefore it should be 1 plus 6j, and option 3 corresponds to the correct answer. Therefore the accurate conjugate of AZ is given as 1 plus 6j plus 7 minus 6j times Z, complex conjugate of Z inverse. Okay, everything is fine. Actually, these questions might look simple, this concept of conjugate and paraconjugate of the given transfer function, of course, but it is actually to prepare yourself to deal with when we'll see the question regarding all pass filter. This conjugacy and paraconjugacy concept are actually going to help you in understanding different all pass all pass fundamental behavior of an all pass filter, or the properties that is crucial for a transfer function to satisfy in order to qualify as a all pass filter. So we'll encounter them in the problems. in later slides. So now this is almost similar to the previous question, only difference is that instead of conjugation we have paraconjugation in the question given problem. So what is the difference between conjugation and paraconjugation? Actually, paraconjugation satisfies the conjugation property that is there. At the same time, it also serves it also have additional property, which is you need to replace Z with complex. So let me write down the inverse part first. Actually, there is slight overlap between these two conditions. They are not exactly separate, because when I say that you replace Z with inverse complex conjugate, and the conjugation actually takes into account the complex conjugate of Z, so therefore these two are not exactly separate, but forgive my explanation here. Actually, paraconjugation can be seen in a slightly better way if we, instead of conjugation itself, we use coefficient conjugation. Actually, in this case these two are separate, these two operations are separate. I'll explain why just in a minute. Suppose Hz have this expression a1 plus a2 z inverse. Therefore, coefficient conjugation, what it does, it only take the complex conjugate of coefficients, that is a1 and a2, but it doesn't do anything to z. So coefficient conjugation actually result in this. Whereas conjugation, which is slightly more general, along with coefficient conjugation, it also takes into account the z as a complex coefficient and takes it complex conjugate. And paraconjugation is of course the most general scenario, kind of. It not only take complex conjugate of coefficients, it also replace z with its complex conjugate inverse, that is this, resulting in a1 star plus a2 star z star. So you see, rather than this way of understanding paraconjugation. This would be a better thing because these two are mutually separate operation. There is slightly overlap between this conjugation is a conjugation. We also take we replace z by z star, which represent the complex conjugate of z. Therefore, saying that replace z with its inverse complex conjugate is kind of give you a overlapping sense. That doesn't a perfect way of explanation. A good one to understand is that you perform complex conjugation which doesn't take into account any changes in z, and then you as a property of paraconjugation you replace z with its inverse complex conjugate. So for the problem, the question in given problem, hz is given as 1 minus 6j plus 7 plus 6j z inverse. Therefore the paraconjugation let us denote is that h2 of z the modified transfer function, of course. Neither as per the notation followed in lecture, we denote paraconjugation by h tilde of z. So it consists of following steps. You take complex conjugate of coefficients and you replace it by its inverse complex conjugate, that is 1 over z star. The resulting transfer function is the following. So let us check which of the options are correct. You can see the fourth one is the correct answer. We next move to a question which at last comes to the property of all pass filter, and we have seen the all pass filter. The question says the all pass filter Hn of z is of order n, which has a pole at z is equal to a naught. The answer, the solutions are regarding the zero of the given transfer function, regarding the position of accurate position of zero of the transfer function of this all pass filter Hn of z. Okay, so all pass filter, let me write down. By the way, we can get the answer of this question by using the critical property of all pass filter, that is your poles and zeros must form a inverse complex conjugate pair. That is a mandatory condition to be satisfied for a transfer function to qualify as all pass filter. So by that property we can immediately give you the answer, but that renders uh, the why this exactly happened. Like you can always find the you can always answer objective kind of answer by that, but you won't have the basic understanding of what's exactly going on inside all pass filter, or what are the uh, properties which enforce this condition need to be satisfied for all pass filter, that the poles and zeros should form a inverse complex conjugate pair. So we'll try to investigate that. Of course, the lectures week 7 has given you already a very uh, thorough treatment regarding this. We'll just revisit some of the crucial properties from there to establish that okay, we are doing correct only. So there are few things to observe. You see, it is said all pass filter Hn of Z is of order n. So this Hn is the transfer function of all pass filter, which is of order n. When we see that, what are the immediate things that comes to mind? This transfer function is a ratio of polynomials at numerator and denominator. And when you say that the transfer function Hn is of order n, that means numerator polynomial is of order n. At the same time, denominator polynomial is also of order n. Now this understanding is crucial. So let me write down the numerator polynomial of order n. Actually, these are not very generalized expression. We are writing in the context of all pass filter only. This is Az represent the numerator polynomial of all pass filter. Of order n, that is start from a naught times z inverse, continue like that up to a n z to the power minus n. By the way, seeing this expression, you immediately see this is a causal filter. I mean, talking about numerator only. Why? Because the coefficients of this coefficient corresponds to these coefficients are actually impulse responses of Az, and this corresponds to non-negative time index, since it's a discrete time filter. This corresponds to non-negative time index, that is an is 0 for n less than 0. So there is no coefficient non-zero coefficient particularly corresponds to negative time index, that is there. Now for all pass filter, this paraconjugation plays a crucial role. Paraconjugation of AZ, not paraconjugation exactly, paraconjugate of course. Paraconjugate of AZ, which we denote as A tilde of Z. We know what to do. We take the coefficient conjugation, that is take complex conjugate of all the coefficients, that is we replace a0 by a0 star, a1 by a1 star. On top of that we take inverse complex conjugate of Z instead of Z and replace it. That way we get a1 star 1 over Z star minus n. Oh, I guess I made a mistake here. Sorry about that. Paraconjugation is about replacing Z by 1 by Z, not complex conjugate of Z. Extremely sorry for the mistake. Actually, this is going to have a ripple over effect. I've done the problem. I've done the mistake in the earlier problems as well. Let me correct them also. Okay, paraconjugation is about replacing Z with its inverse, not inverse complex conjugate. Please forgive me for this error. You should not do that. So let me re-highlight the paraconjugation here. Paraconjugation consists of two properties. You can, let's say, two mutually separate one, that is coefficient conjugation, that is you uh, take the complex conjugate of complex coefficients, and you also replace Z with its inverse, but nothing about complex conjugate of Z here. So this is not a very correct way to explain, because here conjugation actually results into ending up taking complex conjugate of Z also, then replacing Z with its inverse. It's not at all a correct explanation, so this is not a correct one. You should see paraconjugation as a combination of two these mutual separate properties, that is coefficient conjugation and replacing Z with its inverse, and the answer should come like Z, that is paraconjugation. This modified transfer function h to Z takes a complex conjugate of the coefficients and replace Z by Z inverse, therefore you get this expression. Okay, big mistake from my side. Okay, so we get paraconjugate of AZ by A tilde of Z to represent. Actually here also, instead of writing, okay fine, anyway I have written H tilde of Z. So A tilde of Z, you have a complex conjugate of coefficients and place Z over Z inverse. So what you obtain as a result, is this. So when you observe this expression, you can immediately see its filter response or filter transfer function of, of a non-causal filter, transfer function of a non-causal filter. Why? Because this coefficients n corresponds to uh, negative time index. Why I am saying that? Because if you compare the actually the normal transfer function, how do you write? You write Az is equal to h naught plus h1 of z inverse plus up to hn of z to the minus n for nth order filter, right? So this n corresponds to nth time index, positive time index, whose coefficients are z to the power minus n. So if you compare between those two, right, therefore the thing an star z to the power n can be written as a change of variable minus of n tilde z to the power minus of n tilde, right? Sorry, let me correct here myself. Okay, so yeah, we can write that for n tilde is equal to minus n, right? Therefore your impulse responses, that is hns, are non-negative for n negative time index. That is, this expression is actually non-causal. What are the easiest way to get it back into a causal transfer function? For that, you multiply both sides with z to the power minus n. It's a good way of visualizing, as z to the power minus n corresponds to delay by n units. So your transfer function, this a tilde of z, is actually spread to minus nth time index when you try to visualize in terms of the impulse response. And so if you delay by n unit, it actually come on the non-negative axis, come on the right side of the time axis. So in that way it becomes causal. So you can visualize it in both ways, like in mathematical form also, and what exactly is happening. So we obtain star z to the power minus n 1 star z to the power minus n minus 1 up to an star, and this is a causal. You can say this coefficient corresponds to non-negative time index, and there are no non-zero coefficient which corresponds to negative time index. That satisfies the property of causality, of course. We can also write it in just a slightly different manner of writing only. Nothing else changed much. So this az and a tilde of z might look slightly out of context in the question, but this is actually written because in lecture also you have seen the nth order all pass filter transfer function is written like this only: h and z as some constant times z to the power minus n a tilde of z by az. So I mainly bring up the uh, this az and a tilde z thing just to use this property, just to connect between these two. What I think by now you exactly know, because I already given you a hint here that all pass filter of order n can be seen as a ratio between two polynomials of order n. So but these two polynomials has some kind of exact structure especially for all pass filter, and this is the structure you have. You can, that is, they cannot be some two random polynomial, of course that is not allowed. So if your denominator polynomial is az, your numerator polynomial should be a tilde z, which is paraconjugate of z times z to the power minus n, where n is the order of the filter, and that multiplies with some constant k, which is a scalar term. So if we write the expression from above, we'll get this. Okay, we make this equation 1 here, and we need to add a new slide here to explain further. Okay, just remember this expression. We are just going to use the denominator expression later, because by the way, just a small thing that when you talk about pole of a transfer function, pole of transfer function hz, some pole maybe like denote zp, that means your polynomial at the denominator when evaluated at zp comes out to be 0, because when your denominator becomes 0, that's when your transfer function goes infinity. So what is the denominator of your all-pass transfer function? You have seen az, that is az when evaluated at z is equal to zp is 0. Similarly, 0 of transfer function az you can denote as zz. What is the transfer function numerator? And 0 of hz transfer function corresponds to when your numerator polynomial is evaluated at that certain point, your numerator polynomial should go to 0. That is when your transfer function goes to 0. So in this particular case, for all pass filter, we have seen your this, just a minute, yeah, your numerator is z to the power minus n a tilde of z. So z to the power minus n a tilde of z. In this particular case of all bus filter, when this evaluated at z is equal to zz, this should go to 0. So these are the um, relation between the poles and zeros and the numerator denominator polynomials. So when the question says that Hn has pole, sorry, Hn has pole at z is equal to a naught. So that means a z evaluated at z is equal to a naught, that is a naught is equal to 0. From the expression of az here, this expression, what we can write, you just replace z by a naught, that's all. Okay, I guess since the coefficient a naught is already there, I should call it alpha naught. Okay, z is equal to alpha naught is the pole location. So you have z evaluated at alpha naught comes out to be 0. So let me write down the expression of az here, a naught times a1 z inverse. Instead of z we will put alpha naught inverse plus dot 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 up to, sorry about that, a1, sorry, an nth coefficient, n plus 1th coefficient, alpha naught per minus n is equal to 0. Now if I take complex conjugate on both sides, by the way, taking complex conjugate mean coefficient conjugation, and also take conjugate of complex conjugate of z also, which is here alpha naught, of course. That becomes a naught star plus a1 1 by a1 star alpha naught star minus 1 an star alpha naught star minus n 0. You can take alpha naught to the power n outside, to obtain this. Now, do you find any similarity between this expression and the expression here of z to the power minus n times paraconjugate of az? You see, coefficient matches an star here. At the end, a naught star times z to the power minus n a naught star 1 minus alpha naught star to the power minus n. So this quantity, if we compare with the z to the power minus n times paraconjugate of a z, which is nothing but your numerator except the scalar part, of course, this is this term a numerator which is evaluated at z is equal to 1 by alpha naught star. We come from this step to this step. The reason behind playing this trick is nothing but so that we are able to represent this term in a direct relation with this expression for the visual interpretation in a correct way. Of course, this is same as this, but unless you write in this format, you cannot see the direct correlation between these two expressions. So you can see this expression is nothing but the numerator polynomial evaluated at z is equal to 1 minus alpha naught. So here two cases arises. Either z to the power minus n a naught z evaluated at z is equal to 1 minus alpha naught star is equal to 0, or alpha naught star to the power minus n is 0. Correct. Now this, if this condition is correct, that corresponds to alpha naught star to be infinity. Correct. So this is infinite pole. That in our problem, z is equal to alpha naught is a finite pole. It is given. Z is said to be as a pole at alpha naught. It's a finite pole. So this condition, if it requires to be satisfied, this requires alpha naught to be, or alpha naught star, you can both write alpha naught also, they are similar only. Alpha naught need to be infinite. This is an infinite pole problem we encounter, but according to the given problem, the transfer function is a pole at alpha naught, which is a finite pole. So this clearly contradicts with the problem statement. Therefore this one holds, and if this holds, this is nothing but the sorry about the error, let me write it correctly. This is nothing but the numerator of Hn of z. Therefore, if numerator polynomial evaluated at z is equal to 1 over z naught star is 0, that means your transfer function of course goes to 0. Now your numerator polynomial evaluated at certain z is going to 0, that means your hz evaluated at certain z is going to be 0. That is hn of z evaluated, we can write from this, z is equal to 1 minus alpha naught star is equal to 0. This implies 1 minus alpha naught star is 0 of Hz. So you can see the all pass filter property. It is also mentioned in lecture, and of course detail explained there also, that why the transfer function of all pass filter should satisfy this crucial criteria, that the pole and zero should form a inverse complex conjugate pair. So if you have a pole at alpha naught, you should have a 0 at 1 over alpha naught star, and if you have a 0 at alpha naught, you should have a pole at 1 over alpha naught star. So therefore we have seen that H and Z has a 0 at 1 over alpha naught star. So the second option is the correct one. Okay, we next move to our next problem. I think we have done the similar kind of problem in the previous sessions also. It is regarding the uh, finding the type of linear phase filter, finite impulse response filter of order n, and finding certain properties regarding type 2 linear phase filter in this particular question. So I'm going to mention again slightly in details, not too much in detail, so that if someone misses the previous sessions, they can also have an idea from this only. So let me write down linear phase finite impulse response filter transfer function of order n is given as this. Hz is h naught h1 times z inverse up to h n times z to the power minus n. You can see following properties: coefficient of transfer function is nothing but the impulse response if you have written a transfer function in this manner. Therefore coefficients corresponds to non-negative time index that ensures causality order of filter n and number of coefficients. You can also write number of taps of the filter, number of elements in the impulse response is given as n plus 1. So for different type of linear phase finite impulse response filter, this uh, table, short table, which I have drawn earlier also, is pretty helpful to remember, or to for a complex for a compact uh, understanding of this all type 1, type 2, type 3 and type 4 FIR filter at once, if we want to summarize the properties of them. So there are two essential properties, differences between these types of linear phase FIR filter, namely the order and the symmetry of impulse response. You can replace the order with the number of taps also coefficient, because they are essentially the same thing. If one is n, if the order is n, the number of coefficients is going to be just n plus 1. That's all. So there are two actually independent properties. The type 1 linear phase FIR filter order n is even, and the impulse response is even symmetric. Even symmetric corresponds to this. Hn is going to be h naught, that is the first and last coefficients are same. Second and second last coefficient the same, that is h1 is equal to hn minus 1, like that. So it's symmetric around the middle element of the this sequence of impulse response is symmetric around the center of it. That's what it means. So this is type 1. If we move to type 2, the order becomes odd, but the symmetry however remains even, therefore this property is still satisfied. Type 3 onwards, for type 3 particularly, the order is even but the symmetry becomes odd, or in other words we can also write it to be antisymmetric. That satisfies this following property, that first and last coefficients are the magnitude remains same but the sign become opposite. That is, it's you can consider the sequence of impulse response to be in with respect to the center, they have kind of become a invert image of one another. You can visualize this some way. That is, if the sum of these entries are the positive value, then this is the center, the rest of the elements will be in the negative domain, and they kind of form a inverse mirror image in that way, in that sense. And this is the not a very good drawing, but please bear with it. It's important to understand the uh, thing, what's exactly happening. Or symmetry basically means the sequence of impulse response with respect to the center, it the just the inverted image of each other, whereas for even symmetric with respect to the center the sequence, they are just a mirror image of each other. That is the basic difference. And for type 4 filter, it's just that the order is even, n is odd, order is odd, and the symmetry is anyway odd, so this property still holds. It's a minus. Therefore we are concerned with the type 2 linear phase FIR filter. So you can see there are n plus 1 filter coefficients. That's correct, because the order n is to be odd. So this one is also correct, and the impulse response you see is event symmetric. Therefore, all of the above holds true. Therefore, the fourth option is correct. I will take a short 2 minutes break here. Okay, let us move to our next problem. In the fifth question, we have seen our transfer function is z is decomposed in two simpler module, two first order transfer functions basically, and you have input signal xn, discrete signal, a sinc function which is passed through az and to produce output yn. Good. What is the energy of yn? So we are interested in finding energy of yn. So your xn is passed through this LTI system, discrete LTI system, to produce output yn, and from we are going to use Parseval energy theorem here. So what does the Parseval energy theorem says, except of course a mathematical formulation, is that energy of a signal in time domain is equal to the energy of signal at frequency domain. So we are going to use a property in this question what it's mean in the crude sense, that though we are asked in the question as energy of yn, so as if we are supposed to find the energy of yn in time domain, which for a discrete time function for yn nothing but n runs from minus infinity to infinity, norm, or sorry, absolute value of yn square, we are supposed to find that. But instead of that, we'll go to a simpler way. We have this Parseval theorem gives us the flexibility to find the energy of the signal yn in frequency domain also. So we can just as well take the DTFT of a signal yn and find the energy of that. And sometimes, generally, it's easier to find energy of a signal in discrete time domain, especially when you pass through LTI system. You have this flexibility, because in that case, if you pass your input signal xn through this LTI system with the transfer function az to get output yn, your DTFT of output yn, which is given as y to the power j omega, is nothing but the product of h to the power j omega and x to the power j omega, when x to the power j omega is the input spectrum of xn, of course. And the question arises that how we are supposed to obtain h to the power j omega. So you are given hz already, you evaluate this on unit circle, and basically you replace z with h to the power j omega, then you can have its absolute value there. So okay, before, let me write down what we are actually willing to do. So first we write Parseval energy theorem. Its main state, it's as a formal definition, of course, but let us stick toward what is important for us, that is energy in time domain equivalent to energy in frequency domain. So that's theoretical. What is the mathematics we are going to use here? So energy of yn, how we write this up? We write this up like this: n runs from minus infinity to infinity, absolute value of yn whole square. This is nothing but the power evaluated in frequency domain. Where you perform DTFT over yn to get y to the power j omega. You perform DTFT over xn, same, we have x at the power j omega, and you have hz. You evaluate this function as e to the power j omega, you obtain h to the power j omega. So when you have passing your xn through this LTI system with transfer function h of z to obtain yn, you by default have this. Okay, let us first find the x to the power j omega DTFT of input signal. Input signal we see has a specific structure here, 0.4 n pi over n pi is seen from the properties of DTFT as follows. You have sine omega naught n by pi n. If you take the TFT of that, you get a rectangular function basically, and sorry, actually not correct. This rectangular function is 1 for absolute value of omega less than omega naught, and 0 otherwise. So if you are to draw x to the power j omega, which is this, is like this only. Omega naught, anyway, you can see from this comparison, the omega naught is nothing but 0.4 pi. So energy of yn, we denote it as Ey, and from the equation 1 we can write Ey is equal to minus infinity to infinity 1 over 2 pi y a to the power j omega d omega square, by the way. Since we are computing energy, so you got this expression. Keep this in mind, we'll get back to it, but first we need to get h to the power j omega for the given problem. Let me add a new slide here. Let me write down the expression of Hz here. 1 z inverse minus 0.5 over 2 minus Z inverse Z inverse plus 0.5 2 plus Z inverse. Now if we am to evaluate Hz at Z is equal to the power j omega, we can write this as follows: the power minus j omega minus 0.5 by 2 minus e to the power minus j omega, so e to the power minus j omega plus 0.5 2 plus e to the power minus j omega. This we can write as e to the power minus j 2 omega minus 0.25 divided by 4 minus e to the power minus j 2 omega. Now we can write e to the power j 2 omega as cos, summation of cos and sine. So let us write that the power minus j 2 omega minus 0.25 divided by 4 minus e to the power minus j 2 omega is equal to cos of minus 2 omega is nothing but 2 omega only. Sine of minus 2 omega is minus sine 2 omega. There is a I here, or j is more suitable. Minus 0.25 by 4 minus cos 2 omega plus j sine 2 omega. We accumulate the real terms. Now this is the expression of h e to the power j omega. What you have to remember, therefore we get the absolute value of h e to the power j omega square as follows. Nothing, just take the square of real and imaginary term to get a scalar only, no more complex. Numerator denominator both contain sine square plus cos square term. We can safely replace them with 1. Plus 0.25 whole square minus 0.5 cos 2 omega and 17 minus 8 cos 2 omega. Point 0.25 you can write as 1 by 4 also. Therefore we get 1 plus 1 over 4 square minus half of cos 2 omega. Here if you take 17 common, you get 1 minus half cos 2 omega. Sorry, written wrong here. It should remain as it is. 17 minus 8 cos 2 omega. Here it actually becomes 17 by 16 minus half cos 2 omega, which can be written as by taking 1 by 16 common. We obtain 1 by 16, which is irrespective of frequency omega. So H Z here is really a all-pass filter which have the frequency response which is independent of frequency. Of course a scalar term, not 1. If it would have been 1, therefore x e to the power j omega should be equal to y to the power j omega. That is a lossless property, but that actually holds what this all-pass filter Hz has a transfer function of 1. Otherwise it's just a scaled or attenuated version of each other. So therefore if we see from equation 2 what we have, Ey, let me write the equation 2 here again. Ey is 1 over 2 pi minus infinity to infinity h e to the power j omega x e to the power j omega whole square d omega. H e to the power j omega we have seen doesn't depend on omega, so we can bring out that outside as 1 over 16. So it become 1 over 2 pi times 1 over 16. So what is really left to calculate the energy of input signal, which now let me draw the spectrum of x to the power j omega here, which spans from minus 0.4 pi to 0.4 pi, a rectangular function, rectangular window you can say. So this is nothing but 1 over 2 pi times 1 over 16. Your integral spans from minus 0.4 pi to 0.4 pi d omega. You obtain 1 over 2 pi into 1 over 16 into 0.8 pi. This results into 1 over 40. If you compute this, is nothing but 0.025. The energy of the output signal yn is come out to be 0.025, which corresponds to the first answer. Now let us move to the question 6, which asks to consider all plus lattice given in the question and ask the expression for the transfer function. We have encountered similar kind of problem in lectures also. So let us denote these nodes here and here to capture the intermediate sequence. Let us denote as node A and here node B, and sequence here to be UN. So node A equation, what we see that first of all xn gets summed up with the version of un which goes through this block, which basically does nothing because it is a unit gain block. Then it passes through delay and comes here, and we are not going to write them in terms of xn and yn since we are well versed with this z transform of our sequences. We'll write in transform of with respect to z transform of the input signal and also intermediate signal. And since it is not a difficult task because unit gain basically means nothing else, and delay by 1 unit in time domain represent un being un minus 1, whereas in z transform in z domain it just corresponds to z inverse time u of z. So let me write down the xn z transforms to be xz, un z transform to be uz here. uz and yn already been given in question, still for satisfaction I've written that. Okay, so you can see that xz gets added up this version of uz which goes through this unit block and z inverse and multiplied by minus z minus 2, therefore minus z minus 2 times z inverse uz, and they sum up to obtain uz. This gives us xz is equal to uz1 plus z by 2 z inverse, therefore we obtain xz by uz at 1 plus z over 2 z inverse. Similarly at node B, at node B we get following equation, which is you can see here you obtain this version of uz directly come here with multiplication of minus z by 2, so minus z by 2 times uz, the another version of uz which comes through this unit gain and delay block, 1 unit delay block, that is z inverse of uz, they together form yz Therefore we obtain uz times z inverse minus j by 2 is equal to yz. So we obtain uz by yz to be 1 over z inverse minus z by 2. This is equation 2, this is equation 1. Multiplying 1 with 2, we obtain the following. Both side multiplication you do, what you can is this. This implies xz by yz. If you multiply two plus z inverse by 2z inverse minus z, and the transfer function you get just taking the inverse on both sides, that is 2 z inverse minus j over 2 plus j z inverse. So check which of the answer matches. It's the second one. Now we move to question 7. Question 7, you can see your hz is given as a transfer function, first order transfer function, which can be expressed as a product of minimum phase system and all pass filter HAPZ and minimum phase system H min of Z. The question asked what is a possible combination of H min of Z and H AP of Z. So let us move on to check the answers. Before, see, we have multiple tasks at hand. Actually, for each options we will first check whether the product of H min of Z and HAP of Z is giving us the result HZ. If that satisfy criteria, if that satisfy the that okay, product of H min of Z and HAP of Z, the decomposition is correct, that is H min of Z and HAP of Z, the product results into HZ, then only we move to checking following criteria, that whether H min of Z is a minimum phase system or not, or HAP of Z is a all pass filter or not. The first sanity check is for that only. If first we check the criteria of H minimum of Z being a minimum phase system, or HAP of Z is all pass system. These are intensive tasks, and after performing them, if this criteria holds and still H minimum and HAP, the product doesn't result into HZ, that means your all effort is in kind of vain only. So if you first perform the easy sanity check one, and then you move to more complex and intensive task. So for first question, let us check the product of h mean of z and h ap of z minus 1 plus 1 over 4 z inverse 1 plus half z inverse times z inverse plus 1 by 4 1 plus 1 by 4 z inverse. See, this cancel out on the z inverse plus 1 by 4 by 1 plus half z inverse, and this results into 4 times 4 z inverse plus 1 divided by 4 plus 2 z inverse. Now this is clearly not equal to hz, so we need not proceed to check rest of the conditions for option 1. We next move to option 2. We again take the product is 4 times 1 plus 1 by 4 z inverse by 1 plus half z inverse plus 1 by 4 1 plus 1 by 4 z inverse 4 z inverse plus 1 1 plus half z inverse. Okay, this is equal to az, so it satisfies the first condition. Then we will proceed to check the we next proceed to check whether h mean of z is minimum phase system or not. Let me add a slide here also. Need probably 1 or 2 slides. Okay, good. So what is a minimum phase system? Minimum phase system, or what are the conditions for the transfer function of a minimum phase system? So first condition is it should be causal and stable LTI system. Stability basically means your poles should be inside unit circle, and second, not only that, all zeros should be inside unit circle. So let us move to see whether h mean of z satisfy them or not. H mean of z in consideration have this 4 times 1 plus times 1 plus 1 over 4 by z inverse over 1 plus half z inverse. You can see from this expression immediately that for this transfer function, zeros are at minus 1 by 4. Pole, that is actually a 1-0 first order filter, so there should be no zeros, so one pole only. So pole at minus 1 by 2. So you can see the 0 is at minus 1 by 4 and pole in 1 by 2. So let us locate them in Z domain. This is unit circle. Unit circle, norm of Z is equal to 1. Let me denote the pole in a different color. Actually I did wrong. But okay. Here is the pole, here is the zeros. 0 is at minus 1 over 4. Pole it is minus 1 over 2. Okay. So you can see we make these following observations. 0 of h min of z is at z is equal to minus 1 by 4 inside the unit circle, hence the second condition is satisfied. Now we have to show that this is transfer function of also a causal and stable LTI system. So since the causality represents the presence of all the poles inside unit circle, let us first check that. So pole of h min of z is at z is equal to minus half. This is inside the unit circle. So this ensures stability. So presence of all the poles inside unit circle ensures stability. I think I previously told that this is condition for causality. Please, that is a wrong statement. That is error on my part if I have said that. I just feel like I have said that. So please do not take into account. Stability is something, causality is something else that we will proceed to check in the next. But yeah, stability means if the poles of the transfer function are inside unit circles, then the system corresponding to transfer function is said to be stable. So we have seen for this particular transfer function h min of z, the pole is at minus half, which is of course inside the unit circle as we have seen in the figure. Therefore it ensures stability. So we have shown both this all zeros to be inside unit circle, and this is also a stable transfer function. So only thing is left to prove whether the system is causal. If it turns out to be causal, then it satisfies all these three criteria of minimum phase system, being a causal stable system and having its all zeros inside unit circle. So for causality, let me write down the expression of H mean of Z as follows. We see we already have this. We are just trying to get rid of Z term in the numerator. That's what. Now investigate this term, this 1 plus half Z inverse. What does it corresponds to? Let me give you a hint. If we consider a geometric progression series, if you have summation like this, the a plus ar plus ar square dot 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 up to infinity, you get this summation to be a over 1 minus r when r less than 1. Correct? Infinite GP progression series, of course. Now consider a to be 1 and r to be minus half of z inverse. What series you are going to get? You will get 1 minus half of z inverse plus sign comes because minus got squares, therefore plus, their alternating sign will go on, and this will result into this 1 minus of half z inverse 1 over 1 plus half z inverse for absolute value of minus half z inverse less than 1. This corresponds to nothing but z greater than half. So this corresponds to the region of convergence. Region of convergence. This is nothing but the outer region of circle with radius length half and center at and this corresponds to basically this one only. If you draw a circle at center around 0 and radius half, this is actually a region of convergence, this part. So okay, this one we have seen. This is a result of infinite GP series. Therefore we can write this carefully as 2 plus 2 times this series, right? 1 minus half of Z inverse plus half of Z inverse square, like this. Now you can see there is no the exponent in Z, exponents of Z, that Z to the power minus n, all n's are non-negative. In other words, there is no positive exponent of Z. All the exponent of the term starting from Z to the power 0 is 1, of course, Z to the power minus n, where n is a strictly positive term. So exponent of Z is strictly non-positive. Hence, the coefficient of the impulse response corresponds to non-negative time index. This all non-zero coefficients corresponds to non-negative time index. Therefore, Hz is causal. So the expression of Hz that we are getting is a causal. Whose impulse response can be given as this, starting from 0 minus half 1 by 4 minus 1 by 8, like that. Infinite impulse response, of course. Oh, there is a two terms, I'm sorry. There is a multiplication with two terms here. I missed that. 4 plus 2 times this, therefore this becomes, this coefficient got multiplied by 2, therefore it will be minus 1, it will be half, it will be minus 1 by 4, like that only. Okay, there we have proven the zeros inside, all the zeros to be inside unit circle, the pole inside unit circle, that ensures stability, and the third condition is it is also causal, the region of convergence. Therefore H min of Z in option 2 is a minimum phase system. Next we will proceed to check HAP of Z, whether it's a all pass filter transfer function or not, which is given as Z inverse plus 1 by 4, Z inverse plus 1 by 4, 1 plus 1 by 4 Z inverse, 1 plus 1 by 4 Z inverse. Now you evaluate at each AP and z is equal to the power j omega. And to the power j omega, we can directly write cos of j omega, sorry, cos of omega cos of omega minus j sin omega plus 1 by 4 and 1 plus 1 by 4 cos of omega minus 1 by 4 j sin of omega. Therefore you aggregate the real terms and should be minus here. Therefore we get absolute value of HAP to the power j omega as square root of cos omega plus 1 by 4 whole square plus sin square omega divided by 1 plus 1 by 4 cos omega whole square plus 1 by 4 sin square omega, so it would be 1 by 16. This corresponds to cos square omega plus sin square omega plus half cos omega. Here it is 1 over 16 sin square omega. Oh, there is one term 1 over 16 here. Square omega plus 1 plus half cos omega. This corresponds to 17 over 16 plus half cos omega. And same here, actually the square root covers the entire A. It might send a wrong message here, so let me just try to cover the square root entirely. Yep, it's correct. So this is 1. So in this case, this is the lossless property of all pass filter with transfer function. Absolute value comes out to be 1 irrespective of the frequency omega. So this is a all pass filter. Okay, for all pass filter you have to satisfy one another other critical conditions also, which is the pole and zero should form a conjugate transpose conjugate pair. Here you have to check that. For that I guess we need to add a new slide too. Let me write it down here that this stands for all omega irrespective of the frequency or transfer function, absolute transfer function. It takes a value of 1. It also corresponds to the lossless property of all pass filter in this particular example. Okay, so yes, but still we cannot say it to be a all pass filter as of now, because we need to see that the critical condition for all pass filter is satisfied or not, that is it's a pole 0, whether it's forming a complex conjugate transpose pair, or in other words, poles and 0 should be uh, 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 reciprocal of conjugate of each other, reciprocal conjugate of each other. Let me write it down. All pass filter pole 0 should form reciprocal or inverse, whatever it is, complex conjugate pair. So what is the transfer function HAP of Z in the question? Let me see from the previous slide. It is Z inverse plus 1 plus 4, Z inverse plus 1 by 4, 1 plus 1 by 4 Z inverse, 1 by 4 Z inverse. So if I'm supposed to draw its pole 0 plot, it comes out to be this. This is unit circle. From this transfer function we can see 0 at minus 1 by 4, and we can see pole at minus 4. The pole is located somewhere here, minus 4, 0 is located somewhere here, minus 1 by 4. So pole 0, the condition, the reciprocal complex conjugate pair, since the pole and 0 are real, conjugate is irrelevant in this case, so they should be reciprocal of each other. So you can see from here 0 and pole are reciprocal of each other, therefore HAP of Z is a all pass system that satisfies the lossless property, as the absolute value of transfer function comes out to be 1. Okay, next question is regarding the capacity of channel capacity of AWG in wireless channel. So the question asks that an ideal power limited communication channel additive wide Gaussian noise with 1 MHz bandwidth and signal to noise ratio of 15, transmit the information at theoretical maximum rate. So if you remember from lecture, theoretical maximum rate corresponds to the channel capacity, which gives you the expression or the rate expression at which you can transmit information via this channel with the arbitrary low probability of error. If you try to transmit your data beyond this capacity, I mean higher than this capacity, then the arbitrary low probability of error is not guaranteed. But as long as you are transmitting at channel capacity or less than that, you always can transmit your information with very low probability of error. That is another way of saying that the detection or the correct the probability of correct detection or successful detection or reception is 1. That is the channel capacity, and we obtain the channel capacity expression as channel capacity expression R as B log 1 plus SNR. I am writing signal to noise ratio as SNR here. So as the question, sorry. So as the question says that the channel transmit at maximum theoretical maximum rate, that is we are basically achieving the channel capacity, which is the maximum rate of information that can pass through the channel with arbitrary low probability of error. So okay, this is channel capacity expression. The earlier value of SNR is 15, now it is reduced to 7. So how much bandwidth is required to maintain the same rate? So intuitively you can see from expression itself that if SNR value is reduced, you must increase this B, which is corresponds to the bandwidth of the channel. So your earlier SNR is SNR1 is 15, now your SNR2 is 7. Your earlier B1 is 1 megahertz, and what should be your B2 to maintain the same rate, so that R1 become R2, where R1 is B1 times log 1 plus SNR1, and R2 is B2 times log of 1 plus SNR. So I am again and again writing SINR because that's what I am kind of used to. SINR represent signal to interference and noise ratio, but this is not of concern here. So by the problem statement, we should have both of rate to be equal. Again mistake. SNR1 to be B2 times log of 1 plus SNR2. Okay, we have B1 to be 1, so no need to write it. SNR1 is 15, and B2 we need to find, and SNR2 is 7. Therefore we have log, by the way this is log base 2, should not be confused with natural log base E. So log base 2 16 is equal to b2 log base 2 8. This is 4, this is 3, therefore b2 is 4 by 3 megahertz. Actually should maintain the b1 thing here, otherwise this megahertz thing can make confusion. For b1, for third b1, and since b1 is 1 megahertz, you have your new bandwidth to be higher than that. Actually, intuitively, if you are familiar with the capacity expression, you know that if you are reducing the SNR to make the rate same, you must improve this bandwidth. So from that knowledge only, you can see you can easily cancel out the first and third option, that is 2/3 and 1/3 megahertz, because they are less than the even earlier bandwidth, but you are supposed to use more bandwidth. And anyway, none of this is still option if the higher bandwidth option is not correct, but even from that knowledge you can cancel out 1 and 3, so it brings you down to between 2 and 4 only. So with this I end today's session. We will meet again next Tuesday for our 8th session regarding the problems over lectures of week 8. So thank you all.